right, let's continue our review for the Unit 4 lecture exam by talking about what work is. So I've written down up here two of the formulas that you have to know for the exam. So the formula for potential energy and then the formula for kinetic energy. And now we're going to add another formula. So this one is going to be work. So work W is going to be equal to force multiplied by a distance. This is a way of transferring energy from one object to another. So in that picture up there, you see a person pushing on the refrigerator. So they are exerting a force on the refrigerator. That has the effect, if the refrigerator moves a certain distance r, of putting energy into that refrigerator. So the energy initially is coming from you. You're pushing on the refrigerator, and the energy is going from you into the refrigerator when the refrigerator is moving. Now notice it has to be moving. So if the refrigerator's not moving, R would be equal to 0, and 0 times anything is going to be equal to 0. So you're not doing any work on that refrigerator. No matter how hard you're pushing on it, it has to move before you're doing work on it. Notice the units. It's a type of energy, so it's going to be in joules. So this is energy, this is energy, this is energy in transit. Now there is a second kind of energy that can be given to an object, and that's going to be called heat. So there's two ways of increasing the energy of a system. One is by doing work on it, and then the second mechanism is by adding heat to the system. Now we're not going to worry about heat in this course, but if you do take a chemistry course, you would learn what heat is and how it operates. So you should be able to do a math problem in which you plug numbers into that formula. And then don't confuse work with impulse. So an impulse was when you take a force and it operates over a period of time. So when a force operates over a certain length of time, then what that does is it changes the momentum of the system. Whereas when you apply a force over a distance, that's going to change the energy of the system. Now for this unit exam, you don't need to worry about momentum. So there won't be any questions about momentum on the exam, but it is going to be on the final. So that you do need to know this formula for the final. Okay, then another thing that we learned was if there is no outside force acting on the system, so if F is equal to 0, then 0 times anything is going to be 0, and then that means that the change in energy is going to be 0. And so what that means is, since the change in energy is the final amount of energy minus the initial amount of energy, then you can take this over to the other side, and then what you end up with is that your initial energy, whatever it is, has to equal your final energy. And so this statement right here is going to be called conservation of energy. That you can't create or destroy energy. Whatever energy you start with has to equal the energy that you end with. So we did a couple of examples of conservation of energy. So the first one there is the roller coaster. So this would make for a good essay question. Explain how a roller coaster demonstrates conservation of energy. And so you would say that energy is put into the roller coaster by the motor as it pulls it up to the top of the first hill. So now it's a certain distance above the ground, So what kind of energy does it have if it's not moving? Potential energy. Then as it starts to go down the hill, its potential energy starts to decrease because the height is decreasing. But that means something else must be increasing, and that's going to be the kinetic energy, which means it's going faster. And then when it gets to the bottom of the hill, now it has no potential energy, and all of this energy here has been converted into kinetic energy, which is why it's so moving so fast down here. And then as it goes up this loop-de-loop, it loses kinetic energy, but it gains potential. And then when it goes over, it starts to lose potential and then gain kinetic again. Okay, notice that this height here always has to be smaller than this height over here. Okay, because if this loop-de-loop was bigger, if it was taller, it would require more energy than what you started with. And then conservation of energy would not be obeyed. Well, what about the second picture? So the second picture is showing a wrecking ball. And then normally the wrecking ball is going to be down here near the ground. But then when you start to swing it, if you swing the wrecking ball up to here, okay, notice it's higher off the ground than it was here. So it gained what kind of energy? Potential energy. And then when it slams into the building, that potential energy is converted to kinetic energy. Okay, so that was kind of conceptual questions dealing with conservation of energy. So here's another one. But here is an example of a worked out problem where you're going to say the total energy before equals the total energy after. The total energy before is the sum of the potential and the kinetic before, and then set it equal to these same two equations, but you need to put subscripts on it. Put a F for final, so you'd have the potential and the kinetic before something happens, and then the potential and the kinetic after it happens. And sometimes you'll be able to cancel out the M on it. Sometimes you might need to put the M into the equation. And so you can solve one of these types of problems on the exam. Okay, let's take a break. When we come back, let's talk about the laws of thermodynamics.